It's a solo piece, which is why she wants me to play louder. Now, so this is strings. For our one closed, one open tube, rules are a little different. We still have n. N is still our harmonic number, but only the odd integers. Remember, it's only odd integers. I can't write today. Odd integers. So that f of n equals n f1. Still the same. But remember, it can only be an odd integer. Odd integer. But L and lambda, instead 2, now it's n over 4 times lambda, and this is 4 over n times the length. Now, you can put a half staff, it's fine. But it should all be a half staff. So a little different. Now, how do we use these? I'm actually going to show you a problem today, but it'd be nice if you guys had a calculator out. You guys have a calculator out. You got one, real quick, but to help out with this. But we're going to go through this problem because we're going to see parts of this, not this whole thing together, but you might see parts of it in your things. Anybody need more time? So, please write down this little problem. Two open ends. Most musical instruments we treat as two open ends on that. Make a cup. I'm a clutch with a cone out piece of paper. Make a cup.
That also happens for rap.
What?
Like on hold.
Well, all instruments. It happens to your cello.
Exactly, but I didn't know that happened.
They have it. Oh, yeah, it gets horrible. I mean, it's really fun when your instrument's been sitting in your car. You're going someplace and it's like just totally cold because you got to blow through it and warm it up. Or you're playing outside. Play a few concerts outside where it just never warmed up. It's going to be cold the whole time. Or the other thing, when it gets too hot, really hot days, it doesn't play very well. Sometimes it's hard to get a good tone out of it just because it's so hot and things just aren't working well. Yeah, it loosens, tightens strings. It does. All instruments are affected. It's not just they all do that. Because remember, they're made out. For the most part, we're made out of metal. Metal expands and contracts when it heats up and things like that. Yes, ma'am. Yes, I play in a symphonic band. I play in the East Bay Symphonic Band. The community band. What? That is our name. In fact, by the state of California, that's our name. We have a registered. It's our registered name in the state of California. How many people? We usually run about 60 in the band. I mean, basically, a symphonic band is like an orchestra. You have those strings, they're called a band. And if your orchestra means you have strings. And as our instructor tells us, one string does not make you an orchestra. Every once in a while, we'll have a string bass player. One string does not make you an orchestra. It's basically like clarinets and flutes would play basically like the violin and viola parts. Saxophones tend to play cello parts, things like that. Okay, so let's look at this. First of all, we have the length. The length of our tube, 75 centimeters, but we do not like centimeters, we like meters, right? So we would convert this to meters, 0.75 meters. Shh. The temperature is 35 degrees Celsius. And we're dealing with speed of sound here. So do I need to convert this to kelvins?
No.
Now remember, our formula for speed of sound is a Celsius formula. Celsius formula. And we want to find F1, F2, F3. So I need F. Basically what I need to find is the fundamental. Well, we already said we find the frequency by velocity, right? So velocity is going to equal lambda F. Which means I need to be able to find lambda, and I need to find V. Do I have a formula for V? Didn't you use a formula in lab? We have a formula for the velocity of sound. Do I have a formula that I can find lambda, especially since I have L?
Yes.
Yes. Now, since this is an open tube at both ends, lambda equals what?
Oh yeah, wait. N over 2. N over 2.
No, it should be the other way.
2 over N.
2 over N.
That's why I was confusing with the L there.
I'll see if you guys are paying attention.
Okay, cool. I was paying attention.
So we have our formulas here. So once I find lambda, once I find V, I can find F1. And once I find F1, to find the other harmonics, I'm just going to multiply by 2, 3, 4. I'm not going to actually do that part today because that's kind of easy. You find the harmonics. So first of all, we have our velocity. Velocity is going to be that 331 meters per second plus 0.6 t, or 331 plus 0.6 times 35 degrees Celsius. And what is 0.6 times? What is 0.6 times 35? 21. It is 21, which means the speed is going to be 352 meters per second. So there's our speed. Any questions? Okay, this is the calculation you guys did in lab, like 5 or 6 times. The next part says lambda equals n, oops, see, I almost did it again, 2 over n L. And what harmonic are we talking here that we're trying to find? First, we're trying to find the first harmonic, or the fundamental. So this is going to be 2 times 0.75 meters, or 1.5 meters. Any questions so far? So the third step would be to find V equals lambda F, which means F is going to equal V over lambda, which is going to be that 352 divided by 1.5, which is, anybody got an answer for me? 234.66. Or I rounded off, 234.7 hertz. So there is our fundamental frequency. That would be the fundamental. Fundamental. Okay? And so the second harmonic would be twice that value. The third harmonic would be 3 times that value, and the fourth harmonic would be 4 times that value. All right. Any questions? Yes, ma'am.
What was N though? Why did you figure out what the
Where?
the one right above the
2 over
This
N.
one?
Yeah.
That one.
Right there, yeah.
This one?
So what's N?
It's the harmonic number.
Oh.
And since we're looking for the fundamental, it would be the first harmonic
Yeah, that
number.
makes sense.
All right, so you can put that way. That's kind of, we're going to work a couple problems next time. Remember, the test is on Thursday. We're going to watch 15 minutes of review, and then we'll probably have time for another thing. So we're going to just watch the first 15 minutes here. Take notes, we're going to turn in. It's about gravity. In fact, it's talking about the inverse square law. It has a lot to do with what's going on in the world today with tsunamis and stuff like that. And then at the end, we can talk a little bit about tornadoes. Got your book, just kind of bring it back too.
Okay, let's begin. What are we going to talk about today? Right. So you go to a concert. At the concert, you're moved. Emotionally, you are moved. I mean, the music comes and you feel good. You can get into it. You're a part of it. You might even be moved, the eyes watering up a little bit. Sometimes it's so beautiful. And as this is happening, you realize the musicians down below there, or up in front of the thing, are all following some sheet music. And that sheet music can be given to different musicians.
You have one of my books, we can bring it back.
Look at that sheet music and they can do the same.
It's Gravity 1. Call this Gravity 1.
It's really nice. That this emotional
Gravity
response, this ability, comes from a pattern that's on pencil and paper.
1 and 6.
And look at the patterns, it's very complex. And if you're not into music, it looks like, wow, it's just gibberish. But the musicians are trained to read that pattern. And then you get out of the city and you go up country at nighttime and you're looking out at night where there's no moon. The moon's on the other side. And you look out and you see the Milky Way. And you see all the stars. And you see more stars than you can see when you're in the city. That's because the city lights, of course, light up the sky, and the sky is reflecting light. And only the brightest stars will show through it. But in the country, you see many, many, many. And sometimes you also are moved. You get that sort of emotional, all of a sudden you're connected, all of a sudden, and you're not quite connected, and you start to wonder. And you